Okay, hello everybody. Just going to de-fluff myself before the live stream properly begins. I hope everybody out there is doing okay. Again, this is just another live stream where I'm going to be going through GCSE and A-level physics revision as normal. As a lot of people will know, I tend to do the GCSE for about the first half an hour between 7:30 and 8 o'clock. That's kind of like UK summertime. And then from 8 o'clock, we're going to be doing some stuff for A-level. So welcome to everybody. If you're A-level, do come back in half an hour. But for the GCSE crowd, hello everybody. Matty, Matthew, hi. I hope all of you are doing well. Now tonight, we've got some questions which are about, I think it says in my live plan what's coming up. But the questions we've got today, if I just show you, we've got something to do with electrical circuits. So looking at some components about some circuits here. Then there's kind of this kind of experiment over here. And then the second question is looking at springs and how we can actually calculate energy. So hello to James, Zeno, Anissa, Katsuri, hello. Quite a few people there I've seen in the chat many times. But of course it's great to welcome so many new people into this. So let's just get started really. And of course, as we're going through this, I'll keep an eye on the chat. I'll try and answer as many questions as I can. So apologies if I don't see your comment or read it out. But it's great to have so many people there. And of course, if you want to kind of catch up with the previous streams, you can find everything over at GCSE Physics Online. Hello, the slow-mo. Right, so on the left-hand graph, add the line you'd expect if a resistor with a higher resistance was investigated. And on the right-hand graph, draw the shape you'd expect for a filament lamp. Okay, so the first thing is we want to have a resistor. Let's just say that this resistor here has a resistance of R. Okay, so I would say that you've got to remember some of the equations. And one of them, which I think is the most important equation when it comes to electrical circuits, is V equals I times R. Now, a better way to show that is R is equal to V over I. In actual fact, that's what we have here, where if we wanted to define the resistance of something, it's just the ratio of the potential difference across it to the current through it. Now this line here shows a particular value of fixed resistance for this fixed resistor that we have over here. Now let's just look at a point on the line. Let's look at this point over here. When you've got this potential difference, I'm just going to draw a line down to that. When you've got this value of potential difference, that causes this value of current to be flowing or moving through that circuit. Now, if you have a higher resistance, so let's imagine we had another resistor that has a bigger resistance. If it's got a bigger resistance, that means for the same potential difference, we would have a lower current flowing through that circuit because there's a higher resistance. And that means for this value of potential difference, we'd have a lower current, maybe a value a bit like that. In actual fact, if we had a bigger potential difference, we'd still have a lower current than what we see on that line there, and every value is going to be lower. And of course, because it is a fixed resistor, the resistance is going to be constant, so there's going to be this constant relationship between V and I. So what we should be drawing is a line that is straight, it's through the origin, but it has a lower gradient. Okay, so we can see here that for the same value of potential difference, the current is going to be lower on this second line. So this is the line that we'd show. When it's a higher resistance, the line tends to be like this. If we had a resistor with a lower resistance, that would then, in this case, have a steeper gradient. Okay, by the way, just going to read some comments. Hello everybody. So lots of new people joining the chat, which is great to see. Yeah, so is that Sadhu, Sadhu Matix? So I don't know how to, honestly, I don't know how to say some of your names. Temadola, hi there. Yeah, so basically, when we've got this fixed resistor, the gradient is going to be a lower gradient when we've got a higher value of resistance, and that's this kind of ohmic conductor. Now, of course, a lot of people said about S-shaped stuff. If we have this filament lamp, we would have like this kind of S-shaped curve that goes through the origin, and it's going to be like this. Okay, whatever the value of V and I are here, we'd have the same value if that current was going in the other direction. just Sadhu. Okay. Maxi B, do I make money from these streams? Unfortunately not. I think I made about £3 the other week when I had a couple of people doing like super chats and stuff. So if you want to donate in the chat, that's great. The way that I do make money though, and obviously at the moment, all of these live streams are completely free for you to view. And obviously I'm spending the time here doing this kind of every evening. But if you want to support the work that I do at Physics Online, so my YouTube channel and my websites, then you can either buy a subscription to a premium plan on my GCSE website, or you can buy a set of these practice papers, and that comes with the questions, a mark scheme, and also work solutions as well. So if you want to support the channel, I do have stuff at GCSE Physics Online. And people say like, Temadola, yeah, buy the papers, yeah, definitely. So this one over here, we're going to have a couple of marks. You'd have a mark for doing a straight line. You'd have a mark for having a lower gradient, and you'd have a mark for this kind of sort of S-shaped curve. Or I suppose somebody said as well, Abinayan, F, yeah, it's like an F shape as well. I guess F or S. Yeah. Right. By the way, people asking about how you can buy the papers. I put a link that's kind of pinned to the top of the comments in the live, and that's physicsonline.shop. So quite a nice cool domain, I think, physicsonline.shop. And that's my Shopify thing where you can buy digital downloads. Okay. We then have the circuit set up. So this one over here is looking at the IV characteristics of a diode. This diode over here will only let the current go in one direction. State the mistake they have made and describe how they should correct it. Now they've got an ammeter in series, so that looks good to me. We've got a resistor, which you always want to have in series with a diode. We've got a variable resistor, so we can change the size of the current going through this. But here, they've put the voltmeter across the terminals of the cell. As Slow-Mo said, the mistake that they've put the voltmeter over the cell. Now that would only measure the potential difference across this. And say, for example, it was a 6-volt battery, no matter what else is going on in the circuit, that would always give a reading of 6 volts. So the mistake is they've put it there, where really we need to have the voltmeter in parallel with the component that we're actually investigating. So yeah, Slow-Mo said, and Feather as well, the voltmeter should be across the diode. Matty said that as well, it is parallel. Sadhu, yeah, the voltmeter should be in parallel to the diode. I think James Stevenson has got the best answer so far. So basically, we can say that the voltmeter should be in parallel with the diode only, not across, I'm going to call it the battery because we have multiple cells there and that kind of dotted line. So yeah, so the voltmeter should be in parallel to the diode and not across the cell. Okay, thank you very much. Yeah, excellent. Zeno, some great answers here. So I think people have got some really good answers. Why does it have to be in parallel? Ideal. Yeah, so basically the voltmeter always goes in parallel, and effectively it's saying what is the difference in the electrical potential between this point in the circuit and this point. So it's kind of like saying we know that there's a certain potential here, an electrical potential. There's going to be a different electrical potential here, and it's the difference in that electrical potential which is our potential difference. Okay, yeah, there we go. I think people are saying 9 days till their first exam, just over a week. It's about to get real, people. But you're all going to be fine. If you're watching this tonight, I can see there's a lot more people in the chat tonight. So I think that the nerves or the anxiety or the kind of stress or just the excitement is actually starting to kick in. Okay, the next question. The student corrects the circuit and records the data. So we've got different values of potential difference, different values of current. Describe the relationship between the current through the diode and the potential difference across it. Okay, now again, this one is a 2-mark question. Okay, so describe the relationship between the current through the diode and the potential difference across it. I think what we can see is when you've got a bigger potential difference, the size of the current increases. Okay, and the other thing is that normally we kind of see this on a graph. So normally you'd have an IV graph and you'd have data plotted. So you'd see a curve that kind of looks like that. Okay, so again, this is the kind of curve that all of you should be familiar with for a diode. Okay, but we've just got some numbers here. So I think what people are saying here is some people are, I think everybody's correct, is that we can say that as the potential difference increases, the current increases. And you could also say after 0.50 volts. So if we've got numbers there, it's always good to actually kind of quote the numbers. But the other thing you can say is that they are not directly proportional. So it isn't if you double the current or you double the potential difference, we double the current. There's not this kind of double-double relationship. So Matthew said that they're not directly proportional as they don't increase by the same amount each time. You could say that maybe there's this increasing thing here, and you can see that we go up by a very small value of potential difference. So we've gone from 0.75 to 1 to 1.25. So we've gone up by 0.25 each time, but yet this goes up massively from 4 to 15 to 51. Now they would only be directly proportional if they went through the origin and the line was a straight line, but instead we've got a line that kind of steeply curves up. Okay, right. The student then measures the current for several negative values of potential difference, state two changes to the circuit, either of which would make the potential difference across the diode negative rather than positive. So how can we do that? Well, again, here's the circuit. I just left it on the floor. How do we change that? Well, one thing we can do is we can reverse the direction of the battery or the cell. So we just basically have this instead going the other way around. So you can flip the direction of the cell. The other thing you could do would be to flip the direction of the diode. And now, because we have the diode flipped around, that's effectively the same as doing this. And we then have this negative potential difference across it. So you can flip the terminals. Change the direction of the diode or battery. Zeno, excellent. Hello, so switch the direction of the cell, switch the polarity, Thruxy. Hopefully that's all good. So you could basically reverse the direction of the cell or diode. Okay, and the other thing is that just because it's a 2-mark answer, it doesn't mean that you need to fill the whole space. I think sometimes people write too much and then they often contradict themselves. So we're talking about reversing the direction of the cell or diode. Okay, so we've got maybe a mark for the cell, a mark for the diode. That's all there is to. Right, state the value of the current you would expect when the potential difference across the diode is minus 1.0. So because it's a state, that means there's going to be no calculation, otherwise it would say calculate. And we just want to know the value of the current when you've got this value of minus 1. Well, because we've now got a negative potential difference across it, the diode will effectively have an infinite resistance, and therefore the current through it is going to be 0. And I can already see people in the chat saying 0, 0, 0, 0. Yeah, and that would be amps, so 0 amps. Okay. Right, we've got a few questions. At what point will a diode stop current from flowing in the opposite direction? Well, basically, we've got 0 current at 0 volts and 0 current at 0.25. So if you look at this over here, even at very small positive values of potential difference, we still have a very, very high resistance and there's no current. And it's only when we get to a certain threshold voltage, as we call it, that we actually get that current flowing. Okay, sorry, so many things. Yeah. Right, I think that one there was all right, wasn't it? Was that the last part? Okay, so we're now going to go on to a different... Oh yeah, sorry. Does it matter if it's inside or outside the circuit to be classified as parallel? Yeah, basically you could put the voltmeter here, or you could put the voltmeter on the inside. It's just there's no definite way of doing it, and both of these are completely correct. What's important about things being parallel is if we have, effectively there's this line that goes through the component, and we've got this other parallel line to it where we have the voltmeter. So rather than having the wires joined end to end, if we've got wires sort of going side by side, that's when we have part of a parallel circuit. Right. Okay. Right, next question then. So the next question, I'll just leave it here for you all to have a bit of a read. So we've got a metal spring, we've got the original length, it's hung vertically from a hook. The spring constant is this. We've then got a 300 gram mass to the bottom. The length of the spring is 15.9. So sometimes it can be useful to maybe like highlight things and underline things. Also, you can actually add numbers to your diagram. So we know here, for example, that the initial length is 10 centimetres. So that's 0.100 metres. So that's going to be the original length. I'm just going to put that as L. Okay. Now afterwards, it's got longer. And the total length now is going to be equal to 0.159 metres. I'm just going to put my units in there as well. And that means that the extension, the amount it's got longer by, I'm going to call that E, is equal to 0.059 of a metre. Okay, does that make sense? So basically it was 10 centimetres, it's got 5.9 centimetres longer. Okay, and then of course we've got the mass here, so that mass down, M, is equal to 0.300 kilograms. Okay, so there's lots of information there. But the question says, describe how an accurate measurement could be taken to determine the extension of the spring. So, put a ruler at eye level and take away the initial length from the extended length to find the extension. I think that's excellent. I would say to kind of make it as clear as possible, what you could do is you could basically clamp a ruler. So you hold the ruler in a stand. So this is our ruler here that's kind of clamped next to it. So the first thing you could say is that you could clamp a ruler next to the spring. Okay, and then of course what you want to do is think about keeping your eye level, which I think is really point. Zeno says about using eye level to avoid parallax error. Says slow-mo as well, so lots of people are saying that. So basically if you want to sort of look at this length here, you'd have your eye, this is your eye looking in this direction, and then as this moves down, that's when you'd be moving your eye down, so your eye is always going to be level with the measurement that you're taking. So you can clamp a ruler next to the spring. You can maybe talk about how you make sure it's vertical, so you could use a set square to ensure it is vertical, and then you can talk about keep your eye level with with the bottom of the spring to avoid parallax errors. Okay, so quite a lot there. My writing's not the neatest. So, what's the difference between parallax error and human error? Adriel, yeah, great question. Basically, parallax is it's basically to do with, okay, so let's imagine that you had a scale that looks like this. Okay, now I'm going to put the red pen in front of this bit of the circuit. Okay, now the camera's kind of pointing down at this. Okay, but if I was to move this downwards, what you'd see is that even though it's still above the same position, it's now not in line with that because we're looking at this from a different angle. And if I was to move this upwards, and I'm just going to make sure that it is over that, and maybe that's kind of slightly off the scale, when it goes up a bit more, this doesn't read where it's actually truly reading because we're looking at an angle. And the best way to avoid that is to make sure that you are looking directly at sort of 90 degrees or perpendicular to the thing that you're measuring. And that's going to reduce this parallax error. Yeah. So somebody says, oh no, somebody's watching free science lessons. Okay, yeah, he's quite good, but I've got stuff as well. Something else you could do is you could add a pointer onto the spring. and this means that the pointer would stay at the bottom of the spring and point closer to the reading on the ruler. Okay, I think actually in my work solutions I have, as part of the paper, I know a lot of you have already bought these already. This is kind of what I have. So I've basically got the ruler here, I've got a pointer on the end of the spring, and your eye needs to stay in line with that. And I said here, clamp a ruler next to the spring, keep eye at the same level to avoid any parallax error. Okay, right. Okay, okay, there's a lot of love for Sean here, which is great. But yeah, so obviously free science lessons. If you are watching, I know you've probably retired now with your millions from YouTube, but if you ever want to collaborate, I'd love to do that. It'd be awesome to do that. Right. Okay, the next question. Calculate the increase in the elastic potential energy of the spring. So this question is a nice one because it's just a kind of calculation. And I reckon most people are going to get the marks for this. Now, my approach would be looking at the data over here. We've got lots of information here, so I want to write it down again over here. Now, we know that the extension is going to be equal to the final length, which was 0.159, take away the initial length, which equals 0.059 of a metre. Okay, so that's the unit there, the standard SI unit. We always measure our distances in metres. We then need to think about an equation. Now, of course, you do all know this, that the elastic potential energy is equal to 1/2 KE squared. Now, if you're not sure, go and quickly check in your data sheet. You know the ones you're going to be having in your exams. Make sure you've got a copy printed out for every time you do a past paper so you know where all the equations actually are on that, so you can just double check. We're then going to put the numbers in. So that's equal to 1/2 times K, which is the spring constant. It says here the spring constant is 50 newtons per metre. So I'm just going to write that down. And again, I could always write this down at the side over here. So K is equal to 50 newtons per metre. So we've got our values we're going to use. We've got the equation. We start putting stuff in. 0.059 squared. Okay, now I would say for something like this, the way I do this on my calculator is the first thing I would do is put 0.059. I'd square that and get this number here. And then I'd multiply that by 50 by 0.5. By 50. And that gives me an answer equal to 0.087025. Now, I've written down the full number on my calculator, and that's might because I might need to use it later. And then I'm going to give my final answer to an appropriate number of significant figures, which I'm going to say is 0.087. Okay, so for this, we've got marks for working out the extension, for selecting the equation, for putting in the numbers, and then for the final answer. And I think what we have here is something to two significant figures, which is like the kind of the data that we've been given for things like the spring constant. So that's why I didn't just write down the full number on my calculator. Right. Is it good to memorise the equations so you don't waste time, Temodola? Yes, I think you should memorise them, because if you've been revising well and looking at my videos and following these live streams and just doing so much work over the last 2 or 3 years, then a lot of the equations you will remember anyway, and that will then mean that you're more familiar with them, so you've got a higher chance of selecting the right equation. Does the first 0 after the decimal point counter the significant figure? No, so the first one doesn't add to the significance. So you could have a number like 0.0000000000087, and this is still to two significant figures. So that's two significant figures. If you had a number instead, maybe we had 0.8700000000, all of these zeros afterwards add to the significance. So actually this number here would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that number would actually be 10 significant figures. So the zeros in front don't add to the significance. Okay, right. Calculate the decrease in the gravitational potential energy of the mass attached to the spring. So for this, I'm just going to go straight to my mind. I'm going to remember that the change in gravitational potential energy is equal to mgh. Okay, do we know the mass? Well, the mass that was actually initially up high, it's got lower, and that mass was 0.3 0.300 kilograms. Okay, we're going to multiply that by g, which is the gravitational field strength, which is 9.8, so the acceleration due to gravity, and the height that it goes through, the change in height, is going to be equal to the extension. So the spring extends by 0.059 meters, so the mass gets lower by 0.059 meters. Okay, so this number here is just the extension that we worked out up here. And again, we just need to put the numbers in. So 0.3 times 9.8 times 0.059 is equal to 0.17346. So the gravitational potential energy is 0.17 joules. Okay, sorry, there's so many people asking questions, which is amazing. Somebody's saying that, somebody's asking about the next live stream, can we look at electromagnetic induction and the motor and generator effect? I will be covering them. I think I've already got my plan now worked out for every single session. So if you want to find out what I'm doing day by day, so you can kind of put that into your kind of revision timetable, you can find all of that at gcsephysicsonline.com/live. Then, of course, people are asking about the mass of the spring itself. I would say, Slow-mo, that the main mass here, I guess that mass we'd say is negligible compared to the 300 gram mass that we have on here. So yeah, we're going to ignore that because what we try and do in physics and science is make things as simple as possible. Okay, right. Suggest why the answers to part 9.2 and 9.3 are not equal. Okay, so this question here, I reckon if you're an A-level person coming in for the stream now in a couple of minutes' time, even an A-level student would find that difficult. So what we're saying is that when you've got this spring with a mass on it, okay, and the spring extends and we have some energy then stored in the elastic potential energy store of the spring, that energy now stored in the elastic potential energy store isn't equal to the amount of gravitational potential energy and how much that's changed by. So basically the reason is that not all of the gravitational potential energy of the mass has been transferred to the elastic potential energy of the spring. And the reason for that is that as you're lowering it by hand, so you put the spring on and then you lower it down gently, as you're lowering it, your hand is still applying a force to that. And that means your hand is still doing some work. Okay? And you can basically then say that some work was done, as in work done equals force times distance. Some work was done by the force of weight on the hand lowering it. Okay, yeah. So there's going to be some work done. I guess there's work done on the other external force, like a hand, which lowers the mass down. Because if you just let it go, it would go up and down many times, and then some of the gravitational potential energy would be transferred to the kinetic energy store as well as the elastic potential energy store, and then eventually that kinetic energy store would be dissipated to the surroundings as thermal energy. Okay, so hopefully that helps. Do you have electricity for today? Somebody's asking. Yeah, so I did electricity for the first part of the question. I would say that for anybody watching at the moment, I'm just going to put a link up in the description. And I reckon if there's anything that you're not clear about with your GCSE physics revision, go to the website I've just put in the chat just now. So this is GCSE Physics Online. You can still, or you can find videos about the whole part of the GCSE course. If you're not sure about transformers or electromagnetic induction or Fleming's left-hand rule, then of course you can go there and access any video. I think there's about probably 500 or 600 videos in total now on that website, so that as you're revising you can be confident for that. Also, Matty, thank you so much. The first person to donate tonight, thanks so much. I do appreciate that. Oh yeah. Somebody else says about, thank you for the PDF I sent a few days ago, it was very useful. Adriel, yeah, no problem at all. Yeah, thank you everybody from the GCSE chat. It's been a pleasure having you. I think it's been a lot more people on tonight. I've noticed about double the amount of chat compared to normal, so I think it's like kicking in now, isn't it? The fact that, you know, GCSE starts in about 9 days' time. Thank you everybody. I'm afraid I couldn't answer all of your questions, but again, if you're not sure about anything, head over to GCSE Physics Online, and of course join me again tomorrow night and Thursday night. We'll be here from 7:30. Okay, right, that was the end of the GCSE part of the stream. We're now going to be going on to some A-level stuff. Okay, so we're going to continue just working through some questions. I'm just going to get a quick sip of coffee. Okay. Thank you, everybody. Goodbye. Okay. Daniel saying that I'm the best for carrying their revision. Thank you, Matty, especially for the pound. That's awesome. Bye, sir. Slow-mo, everybody. Good to see you. Right. So the stuff we're doing tonight is a bit different. So I'm not just going to keep going on and on and on about these daily workout books. Year 12, you need to buy some. Buy book 4 and book 3. That will really help you. But tonight we're going to be doing some questions from one of my practice papers I've written. So this one here is actually a paper 3A, and this is some sort of the practical skills that all of you are going to be stressing about and struggling with. And in terms of these questions, what I've done is put together for AQA, I've put together some paper 3As. Now I called these alpha, beta and gamma, so there's going to be, well, there are 3 individual papers. You can download them tonight. I've put a link which is pinned to the top of the chat, and that will basically take you to a page where you can download these. Now, I did this for AQA initially, and then basically I've used the same questions and put them together into a pack. So I've got one which is for Edexcel, and also I've got one for OCR, and each of these packs has basically all the same questions, but rather than having questions 1, 2 and 3, and then questions 1, 2 and 3 and questions 1, 2 and 3, these go all the way from 1, 2, 3, 4, all the way up to question 9. So it's the same questions, just packaged differently. So for anybody watching this, and again, if you are doing stuff in Wales and you want to have a go at some practical kind of questions, you could buy any one of these packs and you'll get the same set of questions. Okay, and of course if you're doing things like CIE, if you're doing international A-level, these will all be useful for you. So that's where these questions are coming from. Now today, I'm just going to go through question 1, and we're going to see how far we get. But a lot of this is very similar to the questions I've been going through for the last few days. So these questions, they're about the physics, they're about kind of how to approach exam style questions. So the first question says, and of course play along at home if you want to, and again, say hello in the chat. I do read the chat as we're going along. State the precision of the micrometer used to make these measurements. So we've got some information about a piece of wire that's used in the investigation. They use a micrometer to record values of the diameter at different positions along its length. So again, just by reading the question, this is kind of illustrating best practice. And basically we've got some stuff here. What's the precision of the micrometer used? So how precise are these measurements? Somebody said, would I recommend, and I think actually it'd be good for some A-level people to respond to this as well, would I recommend covering all the A-level physics content during the summer holidays after GCSE? I reckon you don't need to. I think it's nice to kind of have an idea of what's coming up at A-level, but I wouldn't say you have to try and teach it all to yourself. Okay, Joe Smith, excellent. So the precision is 0.01 of a millimetre. So to get the mark, you need to have the number, and also you need to have the unit. So that's one easy mark. Eva, fantastic, excellent stuff. But of course, don't forget to include the units when we're talking about precision. So it could have been 0.01 of a metre, 0.01 of a centimetre. You've got to make sure that we tie this into the units as well. Okay, calculate the value for the diameter using these results and the percentage uncertainty in this value. Now, I would say, looking at this data over here, what we have is about 0.7, about 0.7, about 0.7, about 0.8 and about 0.7. And I would say that when you see this data, I would say that this is an anomalous piece of data, and therefore I discard that. Okay, sorry, somebody just said that when you search up GCSE revision live stream, I'm everywhere. That's pretty cool to know. Do you know what? I might just, I'll check that later. Also, by the way, for anybody watching this, you might notice, and this is maybe like a really kind of geeky thing, but that's what this is all about, looking at kind of A-level physics, is when you look at my YouTube channel. Okay, so I'm just going to go here to my channel, and you look at the lives I've been doing recently, you'll notice that the colour changes very slightly. Okay, and that just means that you can see that there's different live streams, and as we go on over the next few weeks, we're going to have like a whole kind of emission spectrum. You'll also see that there is going to be a black line, so this one over here has a black line in it, and that's because as you have this kind of absorption spectrum, you do get black lines where certain frequencies of light are absorbed. So as we go on over the coming weeks, there'll be more black lines, and this is part of the Lyman series of hydrogen absorption spectra. Is that a really geeky thing to do? But, well, you know, that's my job. Okay, yeah. So, somebody noticed that, James? Yeah, so you'll see hopefully over the next 2-3 weeks, I've got about another 20 live streams I'll be doing, or 25 live streams. There will be this whole spectrum that will make the playlist appear beautiful. Okay, right. Calculate the value for the diameter using these results. So the value for the diameter is going to be just the mean value of those. So 0.72 plus 0.69 plus 0.70 plus 0.73. We're going to divide that by 4, and that's going to be our diameter. We're going to give it in millimetres. So let me just work this out. So is equal to 0.71 exactly. So that is our diameter. Now the next bit is where it gets a bit more challenging, and I know that people hate percentage uncertainty. What we have here are multiple values, and that means that the percentage uncertainty is going to be equal to half the range of the data divided by the mean value multiplied by 100. Now, to work out the range, it's going to be the difference between the biggest and the smallest. So here the biggest value, because that one's an anomaly, is equal to 0.73. Take away the smallest, 0.69. And that's the range, but then we need to divide that by 2. And we're going to divide that by the mean value that we've just worked out up here. Now, that's going to be equal to 0.04 divided by 2. So that's equal to 0.02 over 0.71. Which is 0.028. We're going to multiply that by 100, and that's equal to 2.812. So I'm going to say that this is equal to 2.8%. Okay, so yeah. So Scarface, the range over 2. Yeah, so basically half the range is equal to the, and this is basically the absolute uncertainty in repeat readings, or if you have multiple values. Okay, now sometimes we might be looking at maybe the precision of that measuring instrument, and that would be the absolute uncertainty in that measuring device, but because we have multiple readings, as we see up here, the absolute uncertainty is now equal to half the range. Okay, so we've got half the range divided by the mean value times 100 gives a percentage uncertainty of 2.8%. Now again, I think that you could probably say, well, that's just the same as 3%. And I think my preferred way of doing things, so that we don't maybe round down too soon, is to maybe just use 2 significant figures when I'm giving my percentage uncertainty. But this is the kind of thing that you probably want to check with when you look at mark schemes of actual exams. Explain why repeat readings are likely to produce a more accurate value for the diameter compared to a single reading. So this question is a GCSE question. There's nothing here that a GCSE student couldn't answer. Why is it we take repeats, is all it's saying. Basically, it allows anomalies to be spotted. So that's one thing. Also, if anomalies are spotted, then that means you can then discard them. And it reduces the effect of random errors. Because again, if you have random errors in the data, it allows you to not only kind of spot them, but also it means you can get a mean value, which is going to be probably closer to the true actual value. Okay, so just a couple of points there. You can write in bullet points if needed, and that makes it clearer for you to know that you've actually answered the points in the question, and for the marker as well. We then have the setup. So it would be good to know how many people in the chat have actually measured the resistivity of a piece of wire. Okay. Did I make a question about Unit 3 Edexcel AS? I don't know, Nice, if I did that one. I've done some Edexcel revision videos. Okay, so a lot of people have done this. Okay, so that means this is just a practical that all of you have done. Okay, using standard apparatus. In this case, we've got a multimeter set up as an ohm meter because it's pointing to the ohm bit. We've got wires which aren't perfect. We've got crocodile clips. We've got this kind of rod that might have some corrosion on the surface, so we don't always get a good correction. This is awesome, right? I think most people have done something like this, but of course, there's more than one way to do it, and using different equipment can still get you the same result. So we've now got some data here. They've got values for the resistance of different lengths of wire, and we need to use the results in this table to plot this data and draw a line of best fit. So the first bit is actually pretty easy. Again, in real exams, they tend to give you the labels kind of already marked, and often they give you some points already marked onto that. So what we just need to do is complete the other 2 points. So at point 85, which is going to be here, it's 3.2. So I'm going to put my little cross there, and then at 100 it's 3.6. So it's basically, at 100 it's 3.6. So that's basically there. Okay, so that one over there, 2 easy marks, because you get basically a mark for just plotting the data accurately. That is something that all of you I know will get marks for. Then of course you need to put in your line of best fit. For the sake of this, I'm going to do it in pencil first of all. And what we've got here is a pretty good line, something like that, I guess. I reckon that you should go back to the y-axis because there's no reason not to. I'm just going to use the whole piece of paper like that. Okay, so I reckon that's good enough to be my line of best fit. 2 easy marks in the bag. So 1 mark for the points, another mark for the line of best fit. Okay, easy so far. Right, the next question says, calculate a value for the resistance per unit length using your line of best fit. So what we want to look at is the resistance per unit length. What does that mean? Well, you know, if you had a meter of this wire, what would its resistance be? And we can work this out quite easily because we've got the resistance here on the y-axis and the length on the x-axis. So the resistance per unit length is going to be equal to the gradient. Okay, someone who says you've never had easy question like that in your test, well, it's going to get harder, don't worry. And this is just trying to kind of build your confidence rather than just hitting you with like the kind of questions that AQA used in the 2023 exams. So we want to work out the gradient, which is going to be our change in y over change in x value. Now I would say always draw a gradient or a line onto your graph. I'm going to go from this point up here down here, and that goes across to this point over here. Okay, so I reckon the change in y value is going to be equal to 4.0, which is this point up here. We're going to take away this value down here, which I reckon is about 1.32 approximately. The change in x value, Well, we want to give our resistance per unit length in meters, but here we've got the length in centimeters. And here I reckon that's 110, so that's going to be about 112 centimeters, so that's 1.12 meters. Take away 20, which is 0.20 meter. So what we have is our units of ohms up here, and we've got a unit of meters down there. And that means when we work out the gradient, we're giving it an appropriate unit. So, right. Somebody's asking some questions which I don't know how to answer. Can I make more definition videos on the TikTok A-level 1? I could do. I've got a plan about some definitions, so I've got some sheets that you can download that have definitions on, but I probably need to add more, don't I? There's a million jobs I need to be doing. Okay, let's work this out. So 4 minus 1.32 divided by 1.12 minus 0.2 gives me an answer of 2.913. So I would say my resistance per unit length is about 2.9 ohms per meter. Okay, I think that's appropriate because the data that was plotted over here was to two significant figures. So we've got the resistance to two significant figures. So I'm going to give my answer over here to two significant figures as well. Right. Use the uncertainty and the resistance readings to add error bars to each of the points on your graph. Now, the thing that gets a lot of students confused, I think, when it comes to the practical questions, especially the AQA paper 3A, and of course there will be equivalent OCR questions, is there's so much text to read and actually kind of work out where is important. Now, it does say over here that the ohm meter on this multimeter measures to the nearest 0.2 of an ohm if we want to measure the resistance. And that means on the graph, when it comes to adding error bars, the error bars must go up and down 0.2 of an ohm, because that's the precision of that reading. Okay, so wherever my graph is, what I'm going to do is, luckily, we've got a nice scale here. I'm going to use a ruler. I'm just going to draw it in pencil in case I make a mistake. So we basically got a line a bit like this, like this. There'll be another one here. Are people talking about the weather in Dubai at the moment? Because at the moment the weather near Bath, where I am, is it's just raining yet again. And I've seen the forecast is raining tomorrow and the next day and the next day and the next day. And I suspect, what's it like in Dubai at the moment? Beautiful weather. Yeah. Okay. Are we doing superconductors this session? No, we're not. We're doing this question here about resistivity. Okay. Why don't I halve the 0.2? Well, because it measures to plus or minus 0.2, we know that each of these readings is going to be plus or minus 0.2 of an amp. So when I've added the error bars onto this, we can see that each reading is plus or minus 2 from the point here. Okay, AB, thank you so much. Right, the next question. So we've added our error bars. Use the error bars to draw the steepest, worst acceptable line of best fit and calculate the gradient for this line. Okay, so we now have error bars and we need to draw the steepest possible worst acceptable line of best fit. So this worst acceptable line must still go through all of the error bars, and I reckon we can have a line that looks a bit like this. Okay, now that's still going through all of the error bars, and this one over here is my worst acceptable line of best fit. Okay, right, Holly Deans, good question. With a gradient, would the answer not be 291 if it was in centimetres, not metres? It would be, or no, would it be smaller than that? Because it would be like 4 minus 1 divided by 100. I think because I've converted from centimetres into metres and I've left ohms and ohms, the reason being that the question had the resistance per unit length in standard SI units of ohms per metre. Okay, so I converted from the data on the graph the gradient from centimetres or ohms per centimetre into ohms per metre. So it's kind of 100 times bigger than the calculated gradient. Okay, does that help? Hopefully. Right, so we've now got our worst acceptable line of best fit. Again, to work out the gradient of this, I'm going to draw in to the line of best fit as normal. I'm going to draw in a very, very large triangle. This time I'm going to go from the very top all the way down to the very bottom. Okay, so what we can see here now is that we've got the line of best fit and we've got the worst acceptable line, and the two lines have a different gradient, and effectively the difference between these two gradients gives us an indication of the error and the uncertainty in our plotted data. So the gradient here, m, is going to be equal to the change in y value, which is 4.0 minus 1.2, and the change in x value, in this case I reckon is 1.07 minus 0.23. Okay, so this is just kind of from the data that I've got on my graph. Of course, if you've done this yourself in a real exam, there'll be plenty of options to it be higher or lower. And if you want to find the questions and the other ones on this paper, then you can download it and you can buy a copy tonight. It's only £3.99 for the paper, or you can get all three of them for just £9.99. It's like, that's the price of like a McDonald's for you and your friend, or maybe not even a full McDonald's meal for both of you. So it's really not too much money. Okay, so we're going to work out this gradient. 4 minus 1.2 divided by 1.07 minus 0.23 is equal to 3.333. So I'd say the gradient for this line is 3.3 ohms per metre. Okay, the next thing we want to do is calculate the percentage uncertainty in the value for the resistance per unit length. So what is the percentage uncertainty in the gradient? Well, this is going to be equal to Scarface. Good question. If you buy the paper, it's a PDF. You get emailed as soon as you buy it. So if you buy it tonight, you will have the paper tonight to enjoy, and then you can use it as part of your revision. Right, the percentage uncertainty in the gradient is going to be equal to the gradient of the line of best fit, take away the gradient of the worst acceptable line, divided by the gradient of the line of best fit. We're going to take the modulus of that, so it's a positive value that we want, and we're going to multiply that by 100. So when it comes to the data here, looking at what we had, the gradient of the line of best fit, or the resistance per unit length, was 2.9. We're going to take away the gradient of the line of worst fit, which is about 3.3, and we're going to divide that by the gradient of the line of best fit, which is equal to about 2.9. Again, it's the positive value of that we need. We're going to multiply that by 100, so it's about 2.9 minus 3.3 divided by 2.9 times 100. I get this to be about 13.8. So I would say that the percentage uncertainty is equal to, is that right? About 17%, maybe, something like that. Okay, what do I mean by the modulus, Jacob? Yeah, so basically the modulus is just a positive value. So here, because we had the best minus worst over the best, because my best was 2.9 and my worst was 3.3, that's actually equal to minus 0.4 divided by 2.9. So actually on my calculator, this gives me a number of minus 13, sorry, that's 14, isn't it? That gives an answer of about minus 13.7 or minus 13.8, but the percentage uncertainty is just going to be the positive value of this. So that's what we mean by the modulus. Okay, so we've got a percentage uncertainty in the resistance per unit length of about 14%, roughly. And of course, when you do this yourself, you will have a slightly different line of worst fit, and therefore your gradient will be slightly different. If the slope of the gradient is negative, that could happen as well. So you could, for example, in the question it said to draw the steepest worst acceptable line, but if you're just told to do the worst acceptable line, you could have done the shallowest line, which again still goes through the error bars, and this blue line is now the other worst acceptable line that you could have had. And I suspect if you took that gradient, it might be different to this gradient, and you'd get a different number. But all we're trying to do is kind of guesstimate or estimate the uncertainty in 2 bits of data. Effectively, if you had really good data where maybe that's your line of best fit and that's your worst acceptable line, if the 2 gradients are really similar, then we've probably got a low uncertainty in that data. If instead you had another graph where maybe this was your line of best fit and that was your line of worst fit, or your worst acceptable line, we can see that here there's a bigger difference in the gradients, probably because the data that's plotted is much worse in terms of the spread of data, whereas this might be like really tight data that's kind of pretty much all on that line. So when you've got a greater scatter in the data, there's going to be a bigger difference between the worst and the best lines of best fit, and that means we're going to have a bigger percentage of uncertainty in that data. Somebody's asking how tall I am. I think I'm 181 centimetres away, I think, something like that. Okay, but it doesn't matter if it's negative or positive. It's only the positive value of percentage difference that we're after. Okay, so the next question says, calculate a value for the resistivity of the metal, include a percentage uncertainty for the final value. Hopefully you can see that, yeah. We want to calculate a value for the resistivity. Now, this one over here, the resistivity, is just a material property. And the resistivity, rho, is equal to RA over L, which equals R over L times pi d squared over 4. Okay. Are you allowed like a 12-inch or 30-centimetre ruler? Yes, of course, yeah. I recommend a clear 30-centimetre ruler, definitely. So this is the equation we're going to use. The resistivity is RA over L, which is R over L times pi d squared over 4. So this is just the area, but we worked out the diameter in a previous part of the question, so I'm going to use pi d squared over 4. And R over L, the resistance per unit length, is just equal to the gradient. So that's going to be equal to the gradient of our line of best fit, which we worked out previously as 2.9. We're going to multiply that by pi d squared over 4. So that's pi times d. And again, this is the difficulty. There are so many bits of paper. We worked out the diameter for the first part of the question, 0.71 millimetres. So that's times 10 to the minus 3 metres, all squared, divided by 4. And when we put that into our calculator, this gives a number equal to 1.1 times 10 to the minus 6. I'm sure you saw that. Don't we have to convert the units for the gradient? Yes, we do. Yes, sorry. So earlier we worked out the resistance per unit length in ohms per metre as part of that previous question. So yeah, so this is now our resistance per unit length in ohms per metre. Okay, so that gives this number over here. That is the resistivity. That's the kind of number we expect. When we look at resistivity, because effectively it's a resistance of a unit cube of that material, we're going to have really, really low values. So 1.1 times 10 to the minus 6. Okay, now the percentage uncertainty in the resistivity is going to be equal to the percentage uncertainty in the resistance per unit length. And we worked that out in the last question as, in this case, 14%. So here, the percentage uncertainty in the gradient, and we're going to add that to the percentage uncertainty in the diameter. Okay, now the percentage uncertainty in the diameter was worked out for the first question as 2.8%. And it's going to be 2 times the percentage uncertainty in the diameter, because the diameter is squared. Does that help? Okay, so to work out the total percentage uncertainty in the resistivity, it's equal to the percentage uncertainty in the gradient, which in this case was 14%. And we're going to add that to 2 times 2.8 that we had over here. Okay, so we just add the numbers together. So 2 times 2.8 is like 5.6. 5.6 plus 14 is going to be about 19.6%, which is approximately equal to two significant figures to 20%. So the percentage uncertainty in the resistivity in this case is about 20%. Okay, does that make sense? Is it 2 times the uncertainty in D because the diameter is squared? Yes, it is, yeah. So we don't work out the area directly, we work out the diameter, or that's what we measure, and then because that's squared, the percentage uncertainty in our value for the diameter is doubled because we've got a squared quantity over here. Okay, use a graph to calculate a value for the resistance of the connecting leads and crocodile clips used in this experiment. So this question here is actually quite a difficult part. Okay, and this is the kind of thing that's going to separate the B grade students and the A grades and the A star students. So basically, on the graph that we had before, we basically looked at resistance per unit length, and if we actually were to follow this back to the origin over here, what we find is if we plotted it, we'd have a graph that looks a bit like that. So even when the length is equal to 0, there would still be a certain value of resistance. And that's because this is like a real experiment where there's a resistance of the kind of the connections, the crocodile clips, the bits of wire, things like that. So the measured resistance is actually RT. That's the total resistance measured, which is going to be equal to the resistance of the wire that we're actually testing, plus the resistance of like the leads and the crocodile clips. So we've basically measured the total resistance, not just the resistance of the wire. And that means if we were to sort of look back when L equals 0, that would be the resistance of the other parts of that circuit. So therefore, this is the resistance at the y-intercept. Now, because we know that y is equal to mx plus c, we can work out the value of c by looking at a value from the line of y, taking away mx, and that will tell us the value at that point. So, looking at this gradient, so well, let's use the value of y. Sorry, there's so many bits of paper here, aren't there? I can't find my graph. Oh yeah. So we look at the line of best fit. Let's just take this value over here. Okay. So when the value on the y-axis is 1.6, we're going to take away the gradient, which in this case was 2.9, multiplied by the x value, which was equal to 0.30 over meter. Okay, so if I do that, we've got 2.9 by 0.3, 1.6 minus this, gives me an answer for the y-intercept of about 0.73. So the resistance, when the length of wire being tested was 0, is equal to 0.73, and therefore this must be the resistance of the crocodile clips and the connecting leads in that experiment. Cool. Hopefully that helps. Right, I'm going to see some questions that people... I've seen that there's so many questions. I'm afraid I haven't had time to answer them all as the stream's gone on. When you halve a value, does the uncertainty need to be halved? Like calculating the radius instead of diameter? I would say that if you were to half a value, then the percentage uncertainty in the diameter is going to be equal to the percentage uncertainty in the radius. Okay? Because it's not the absolute uncertainty, it's the percentage uncertainty of that value, and that percentage uncertainty of that value stays the same. The only time that we would halve the uncertainty was, say for example, let's say we had z equals p times the square root of d. Okay? Now here, the percentage uncertainty in z is equal to the percentage uncertainty in p plus a half of the percentage uncertainty in the value of d. So if you knew that percentage uncertainty and that percentage uncertainty, because we've square rooted, which is effectively the same as saying z is equal to p times d to the 0.5, because we've raised d to the power of 0.5, that's the only time we'd actually half that uncertainty. Why can't I just read the y-intercept off the graph? Good question, middle mip. Is because on the graph, we don't have that as the origin. It starts at plus 20, so we can't read that off. That's not the intercept, that's just where that graph kind of runs out. Okay, my thoughts on the textbook Measurements and Their Uncertainties by Hughes and Hayes. I'm afraid, AB, I haven't read that book. I'm not familiar with it, so I'm afraid I don't have that. Okay, yeah, Ben, Josh, hopefully you understand that this is not the y-intercept. This is like 20 centimetres, so really the y-intercept would be like over here somewhere, wouldn't it? Like that. Okay. Why is x 0.3? Where was that? Oh yeah, for this, basically I just took a value off the line. I could have taken any values off that line of best fit, okay? But I said that my value of y is equal to 1.6 up here. My value of L, or x, was equal to 0.30 of a metre. Now the reason I did that, and I probably should have made it a bit clearer, was because here I had, effectively my gradient was in ohms per metre, and therefore this must be in metres as well, because we're multiplying the two things together, so we've got to have consistent units. If I'd had this value in ohms per centimetre, I'd have multiplied it by 30 to get it in centimetres. Okay, hopefully that's all right. Right, hopefully this also shows you that I do have questions that can help prepare you for practical exams for real A level. So hopefully that was all good. If you do like this, if you want to keep supporting the channel, if you want me to come back, and if you're year 12 and you want me to be back here next year, then keep spending money. That's important. I'm trying to keep it affordable so that, I'd love to make everything free, and a lot of content I do is free. I think I've got about, 1,300 free videos on YouTube. So there's lots of free content. But in order for me to keep doing what I'm doing, your support is absolutely invaluable, and I want to keep the cost down as much as possible. Of course, if you want this completely for free, you can get it. To get it all for free, you need to ask your teachers to buy a school subscription for the whole department, and that means you can watch my whole website for free. And if you want to get these exam papers for free, ask your teachers to buy the school set, and that means your teachers can give it to you. But all the stuff I do can be free for students. You just need to keep badgering your teachers to buy stuff from the school. So hopefully that's all good. I will see all of you again tomorrow night. Yeah, have a good day. Hope your revision is going well. It's not that long until the exams, but I know all of you can make a massive change in that time. Thank you so much, everyone.